Welcome back. Welcome to Module 4. In the last session, we saw how the file indexer worker does the heavy lifting of reading files. But where does all that extracted text go? Storing it in memory isn't an option. It would be lost as soon as the application closes. And we need memory to be permanent, a little bit more permanent than ephemeral. In this module, we will dive into apps memory, the local database. We will explore how we use Room, which is Google's recommended database library, to permanently store the indexed content, and most importantly, how we query it almost instantly. Now let's go through the agenda for today's session. First, we will go through Introduction to Room, where we will understand usage of Android's abstraction layer, which is called Room, and see how we used full text search in our application using Room. Second, we will see our database schema and understand the search by content function. Third, then we will learn debugging with the database inspector, which is Android's application inspector. Then we will practice by adding a file counter to our code. Okay, let's move on to Introduction to Room. That's our first topic. So Room is an abstraction layer over the standard SQLite database that comes with every Android phone. It makes working with the database much simpler and safer. A Room database has three main components. The first is the entity. This is a simple data class that defines the structure of our database table. Think of it as a blueprint for our digital note cards, or it defines the schema. Second, the DAO or DAO, or full form is the data access object. This is an interface where we define all our database queries, like how to insert data or how to search for it. So if you're more of a web application person, then this is where you will define your policy and rules for the database, the data in the database. And the third is the database itself. This is the main class that ties everything together and manages the connection to the database file itself. By using these components, we can compile time checks on our SQL queries, which prevents the whole category of common runtime crashes. So let's move on to the secret to our speed, which is full text search. So how do we search through potentially millions of words of text in milliseconds? A standard database query, like where content like blah, 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 would be incredibly slow. It would have to scan every single character of every document. The solution is full text search table, or FTS. This is a special type of virtual table that creates a highly optimized index of all words in our content. So when we perform a search, we use the match keyword instead of like. This tells the database to use its special index, and the result is a search that is order of magnitude faster. This is the core technology that makes Find My Files search feature instant and speedy. Now, how does FTS work? It works on a fundamental rule or idea of stemming. So stemming is a rule-based process that simply chops off the end of words to find a common stem. For example, running will become run, runs will also become run, runner will also become run. So all of them have the same root or stem. The match keyword in SQL or SQLite's FTS uses a tokenizer. By default, this tokenizer is quite simple. It breaks text into individual words based on spaces, punctuation, and converts them to lowercase first. It can also use an optional built-in stemmer like Porter stemmer, which you use normally in NLP or data science, which performs the simple word chopping as I described above. So when you search, it's matching these simplified stems or tokens, which is why a search for run might find a document with running. However, it does not have the linguistic intelligence yet. We can build it into this application as well. So let's look at our database schema. At our actual implementation in the DB package, we use two entities, a normal file entity to hold the structured data and a virtual file entity FTS that is linked to it and provides the full text search index on the content column. In our file DAO, you can see the search by content function. Notice the query. It searches the file entity FTS table using the fast match operator that we explained previously. and then uses the result to select the full records from the main file entity table. This two table structure is the standard and most efficient way to implement FTS in Room. Now let's understand debugging with the database inspector. One of the most powerful tools for working with Room is the database inspector, which is part of the app inspection tool in Android Studio. When your app is running, you can open this tool to see a live view of your database, which is being generated. You can see the tables, their columns, and most importantly, the actual data inside them. So you can see I have shown the whole picture. This is an invaluable tool for debugging. So the screenshot is from my emulator. When we were building the file indexer worker, this is how we confirmed that the data was being correctly extracted and saved. It takes the guesswork out of database development. Otherwise, you would know the issues only during the final testing. Now that you understand how the data is stored and searched, your task is to add a new feature that counts the total number of files in the database. This will involve two steps. One is to add a function, and then second is to add a query annotation to this function. So you open the file dow.kt file, then you add a function called count files that returns an integer. Then you add a query annotation to this function. The SQL query to count all the rows in a table is select count under parenthesis star from file underscore entity. Bonus is if you have time, you go to the main view model.kt and create a new state flow for the file count and call your new DAO function to update it, which you can skip. So this will give you hands-on experience. You can stop the clock, take your time, whether it's 10 minutes, 20 minutes, or one day, return back to look at the code. So let's look at the code. This code defines a function within data access object or DAO interface in the Android Room database. Its purpose is to count the total number of records in the file entity table. And if you look at the code breakdown, at query, this is the room annotation. It tells the room library that the method below is meant to read data from the database. The string inside the parenthesis is the SQL query that room will execute. And the select count from the file entity was given to you as part of the exercise to be used. This is the SQL query itself. Suspend fun count files int. This is the function declaration. Now suspend, this is the Kotlin keyword that makes this function as a coroutine. It allows the database query to run on a background thread without freezing the application or app's user interface. This is crucial for performance enhancement. Fun count files, this is the name of the function. When you call this function in your code, Room will execute the SQL query associated with it. And the last one, int, this is specific. This specifies the function's return type. So since count star returns a single number, which is the total count, the function is set to return an integer or int. How it works altogether, when you call the count files function from your code within a coroutine scope, Room automatically first executes the SQL query on a background thread. Second, receives the numerical result from the database. And third, returns that number as an int to your code. So let's summarize what we learned today. In this module, we explored the app's memory, the local room database that makes the instant search possible. We did introduction to Room. We covered the three main components of Room database: the entity, the data table, then the DAO, the query interface, and the database class. Then we moved on to full text search, FTS. We learned why a standard database query is slow for our needs and how a special FTS table creates an optimized index to perform high-speed searches for words inside large blocks of text. Then we discussed about database schema. We walked through our database files like file entity.kt, file entity fts.kt, and file dow.kt to understand how the tables are defined and linked to each other. Then we looked at the debugging with the database inspector. We learned how to use the powerful app inspection tool in Android Studio. It allowed us to view the live contents of a database during development, which is crucial for debugging the file indexing process. So let's look at what we'll cover in the next session, which will be Module 5, the backend. We'll move to the cloud and focus on the server side components that power the application's user management and monetization features. First topic would be Firebase authentication. Here we will look at how the application provides secure user login for both email password and Google sign-in. Then we'll look at Cloud Firestore. We'll explore how we use a scalable real-time NoSQL database to securely store each user's subscription status and manage the account deletion queue. Then we'll look at Cloud Functions. We will do a deep dive into our serverless backend code index.js. We'll examine the logic for our three key functions: creating a Razor Pay order, verifying the payment, and handling account deletion requests. Then we'll look at the security best practices. We'll discuss how we secure our backend by checking for authenticated users in every function and how we safely manage sensitive API keys using Google's Secret Manager. And then, of course, we'll do some practice lab. And then we will move on to connecting all the modules together. So thank you again for joining. I'll see you in the next